January 1944. Truck Lagoon, Pacific Ocean. The wreckage of an American bomber lay half buried in the coral sand, its silver fuselage torn open by flak and salt water. The humid air smelled of burnt oil and seaweed as a group of Japanese naval technicians circled the remains in silence. They had expected steel, aluminum, and riveted armor, the familiar language of war machinery. But what they found instead made them whisper in disbelief. A control panel made of a strange brown material. Not metal, not wood. Lightweight, smooth, and unscarred by corrosion. A side hatch handle that flexed under pressure yet hadn't broken. Pieces of cockpit trim that looked like glass but felt warm to the touch. One engineer snapped a fragment in two. It cracked cleanly like glass. But it wasn't glass. Another held it to his nose. It smelled faintly of resin. "It's plastic," one murmured. The word hung in the tropical air like an accusation. A material that shouldn't have belonged on a warplane. Yet it was there, stronger than expected, lighter than imagined. To the Japanese observers, it was more than a curiosity. It was a revelation, a sign that America's power came not only from steel, but from chemistry. Before the war, no one imagined plastic could ever replace metal in the engines of war. Aircraft were built from aluminum, brass, copper, and steel. Each one mined, forged, and riveted by hand in factories that echoed like cathedrals of iron. To military engineers around the world, metal was strength, permanence, victory. But by 1942, the United States faced a quiet crisis. Aluminum was vanishing faster than bauxite could be mined. Brass and copper were being swallowed by shell casings and communication wire. The demands of modern total war were unlike anything industry had ever known. Instead of slowing production, American scientists turned to an unlikely answer: chemistry. In New Jersey, DuPont Laboratories began producing new polymers: bakelite, lucite, and phenolic resins, substances once used for radios and household goods. At General Electric, engineers under Charles Kettering developed heat-resistant plastics that could endure vibration, salt, and sunlight without warping. Soon, cockpit dashboards, bomb bay panels, gun grips, and even propeller cones were molded instead of forged. A bomber that once required hundreds of aluminum brackets now used pressed resin fittings. Weighing half as much, this revolution didn't happen in secret laboratories. It unfolded on factory floors staffed largely by women and young chemists who had never built a plane before. They mixed, poured, and baked the new materials in ovens once meant for car parts, guided by little more than blueprints and courage. Plastic had become the miracle metal, not because it was strong, but because it was enough. It saved weight, conserved metal, and let production keep moving, while other nations struggled to feed their furnaces. By 1943, entire divisions of the War Production Board tracked how many pounds of steel were replaced by resin each month. The numbers shocked even Washington. Every pound saved meant another plane could fly. And across the Pacific, Japanese intelligence began to notice something strange in the wreckage left behind. By late 1943, the Imperial Japanese Navy had begun recovering fragments of downed American aircraft across the Pacific. The pieces told a story that no report could fully explain. Technicians at Yokosuka Naval Arsenal laid out the remains of a B-25 Mitchell that had crashed near Rabaul. They measured, weighed, and cataloged every component, just as they had done with earlier British and Dutch machines. But this one defied their expectations. Instrument housings that should have been aluminum were strangely light and faintly glossy. Switch knobs, instead of metal, were molded from a warm brown material that felt like wood but did not burn. Even structural brackets hidden behind bulkheads appeared to be pressed from something entirely synthetic. At first, Many believed the Americans were experimenting with inferior substitutes, perhaps driven by their own shortages. Yet field tests told a different story. The so-called plastic components resisted corrosion from salt air and survived heat that warped Japanese alloy parts. They absorbed shock during impact rather than shattering, reducing maintenance on long missions. Japanese metallurgists tried to replicate the substance using phenol and shellac mixtures, but none achieved the same strength-to-weight ratio. Reports circulated quietly through the Aviation Technical Bureau, concluding that the Americans had developed a non-metallic material of exceptional resilience, produced in industrial quantities far beyond Japan's capabilities. This was more than a scientific curiosity. It was evidence of a civilization whose industry had fused chemistry with engineering. While Japan's war effort still depended on limited aluminum imports from Southeast Asia, American factories were literally creating new materials to fill their gaps. To the technicians who sifted through wreckage at Truk and Kwajalein, the message was undeniable. The United States was fighting a different kind of war, one built not on scarcity, but on invention. And as those fragments crossed the ocean to laboratories in Tokyo, a realization began to spread through the halls of the Navy Ministry. If America could mold its war machines from plastic, what else might it be capable of shaping? For every bomber assembled in Detroit or Seattle, another quiet battle raged in the laboratories of Delaware and Ohio. Chemists who had never worn a uniform worked 12-hour shifts in rooms filled with the smell of phenol and acetone. Their mission wasn't to build weapons, it was to make resources last longer than the war itself. Inside DuPont's experimental station, engineers mixed phenolic powders with cotton and asbestos fibers, pressing them in heated molds until they fused into bakelite. These resins could withstand temperatures near 250 degrees, enough to line switch housings, radio panels, and gun sights. Across the country, General Electric and Dow were refining transparent acrylics under trade names like lucite and plexiglass. Suddenly, cockpits were clearer, lighter, and safer. Shattered glass no longer blinded pilots in combat. It was a revolution hidden behind factory doors. The nation's chemical industry, once focused on consumer goods, had become a strategic arm of the war. Plastic was no longer a novelty. It was armor, insulation, and vision combined. In a Cleveland assembly plant, the rhythmic hammering of rivets had given way to the hiss of steam presses. Women workers in protective aprons poured powdered resin into molds, locked them shut, and watched the gauges climb. When the pressure released, out came a perfectly shaped bracket. Smooth, strong, identical every time. The shift astonished older machinists. No milling, no waste, no sparks. A process measured in minutes, not hours. Entire components, once requiring skilled metalworkers, could now be produced by newly trained operators. It wasn't just material innovation, it was a social one. The democratization of production mirrored the democratization of invention. Plastic parts turned precision craftsmanship into repeatable manufacturing, freeing manpower for the front and accelerating the flood of war materiel. The same efficiency that allowed the United States to build a bomber every hour now flowed through every resin press. Meanwhile, across the Pacific, Japanese engineers watched reports of these materials with growing disbelief. Their doctrine prized durability and tradition. Steel forged with ritual precision, aluminum machined to perfection. The notion that a synthetic could equal or surpass metal seemed almost sacrilegious. Yet the evidence mounted. Captured fragments refused to rust in humid air. American aircraft that had survived multiple missions bore components that looked brand new. To some technicians, it felt like encountering a new philosophy, one where impermanence was strength. Plastic symbolized flexibility, adaptability, and a willingness to reinvent even the fundamentals of warfare. For Japan, fighting with finite resources and rigid doctrines, This realization was deeply unsettling. At the Imperial Navy's Technical Bureau, senior engineers pored over recovered fragments under magnifying lamps. Their memoranda read like disbelief set to paper. Material of unknown composition. Appears resistant to salt corrosion. Impossible to machine. For men trained in metallurgy, polymers felt like sorcery. What unsettled them most wasn't what the Americans had built. It was what they had freed themselves from. They no longer depended on the finite veins of ore that anchored Japan's industrial limits. Chemistry had become America's new geography. A captured engineer summarized it best. They manufacture strength, not mine it. That single sentence captured the gulf between two worlds, one bound by tradition, the other by reinvention. The discovery forced Japanese planners to reconsider how the United States was sustaining its output. If aircraft parts could be molded from substitutes, then America's supply chain was effectively bottomless. Analysts realized that replacing metals with resins multiplied not only production speed, but logistics freedom. Lighter aircraft required less fuel, fewer replacement parts, and could be shipped in greater numbers. Intelligence summaries sent to Tokyo in 1944 warned that industrial flexibility now constitutes an element of warfare. Yet Japan could not imitate the feat. Its chemical industry, already strained by embargoes and shortages, lacked the raw ingredients and equipment for mass polymerization. The revelation was both scientific and spiritual, a glimpse into an opponent whose creativity had become a weapon. In hindsight, those fragments of plastic foretold the post-war world. They were the first whisper of the coming age of synthetics, an age when lightness, adaptability, and abundance would redefine civilization itself. For the Japanese technicians of 1944, they represented defeat in its purest form, not on the battlefield, but in imagination. Tokyo, autumn 1944. Rain slid down the windows of the Navy Ministry as technicians gathered around a long table. Spread across it were pieces of American aircraft, fragments shipped from island outposts under cover of secrecy. Each bore a small paper tag, handwritten in precise kanji. Material analysis pending. At the head of the table, Commander Shigeru Matsuda of the Naval Air Technical Department read aloud from a translated American maintenance manual recovered on Saipan. The words made the room fall silent. Phenolic resin housing. Resists heat and corrosion. Replace only as a unit. Resin. Plastic. Synthetic. The chemists knew what it meant, and their expressions hardened. They had spent months attempting to reproduce the same composition using shellac, cellulose, even ground nutshells mixed with tar. Every test failed. The samples warped under stress or crumbled in heat. America's version endured. The final report, dated November 12, 1944, summarized the discovery in a single phrase. The enemy has achieved chemical synthesis beyond our current reach. The conclusion was devastating. It meant that American industry could create materials faster than Japan could extract them. Every plane shot down, every ship sunk, could be rebuilt not merely because of manpower, but because the substance of war itself had changed. As U.S. bombers began to appear in greater numbers over Formosa and the Philippines, Japanese officers drew a grim connection. Their opponents were not just stronger, they were lighter, faster, and endlessly replaceable. For the first time, victory no longer seemed a matter of courage or training, but of chemistry and invention. As 1944 turned into 1945, Japan's industrial heart began to falter. Cities once filled with the rhythm of machine presses now echoed with air raid sirens and silence. Aluminum, copper, and fuel were rationed beyond reason. But in Tokyo's laboratories, chemists still worked through the nights, searching for a substitute, a Japanese answer to the American plastic. They tried blending soybean oil with formaldehyde, boiling cashew nutshells for resin, even experimenting with rice husks and lacquer. None of it worked. Their versions melted under sunlight, shattered under stress, or turned brittle in salt air. Each failed sample carried the same bitter message. Chemistry was the new battlefield, and Japan was losing it. Meanwhile, captured American aircraft continued to reveal marvels that bordered on humiliation. A downed F-6F Hellcat near Iwo Jima carried molded insulation panels and transparent domes of lucite, lighter than glass, resistant to shrapnel, and nearly impossible to scratch. Radio sets were encased in bakelite shells that survived fires hot enough to melt aluminum. The reports piled higher on the desks of naval engineers. They no longer read like technical documents. They read like eulogies for a nation's industrial dreams. The final blow came when reconnaissance revealed that American factories were producing plastics by the ton, shipped worldwide without fear of shortage. Japan's supply lines, stretched across collapsing colonies, couldn't even feed its foundries. For every ton of steel Japan struggled to refine, America molded 2 tons of synthetic material from chemical vats. In the words of a captured officer after the war, "We built with what the earth gave us. They built with what their minds invented." That realization, quiet, cold, and irreversible, marked the true turning point. Japan still fought, but the war had already slipped beyond reach. The material of victory was no longer metal, but imagination itself. When the war finally ended in August 1945, Japan lay silent beneath its own ruins. The factories that once forged Zero fighters stood hollowed by firebombing. Laboratories that had struggled to match American materials were reduced to ash. The Empire's engineers, once servants of war, found themselves standing amid rubble that smelled of iron and smoke. Yet, even in defeat, their curiosity survived. In the months following surrender, American occupation forces began cataloging Japan's scientific infrastructure. U.S. specialists from the Technical Intelligence Unit were astonished by the meticulous research. Notes they found, failed formulas, broken test molds, and glass jars labeled phenolic substitute experiments. They realized that even in isolation, Japan had tried to reverse engineer an entire chemical revolution without access to raw components. Now, with peace, those same minds were redirected. Former military chemists and engineers were hired by private companies. Mitsubishi, Sumitomo, Toray, and Asahi Kasei. Their wartime lessons in failure became the foundation of a new mission: to master polymers, resins, and synthetics not for bombers, but for daily life. Within 5 years, Japan began producing nylon, polyethylene, and acrylics, materials once seen only in captured American machines. Plastic, once a symbol of defeat, became a tool of resurrection. The same laboratories that had struggled to mold aircraft parts now molded the future. Radios, toys, and electrical components that would power Japan's post-war boom. Across the Pacific, American industry continued to evolve. Wartime research flowed seamlessly into civilian innovation. Companies that had once built bombers now built refrigerators, cars, and televisions, all with plastic shells and composite interiors. What began as an emergency solution during scarcity became the cornerstone of modern abundance. The war had ended, but the era it birthed, the plastic age, had only just begun. The Second World War had ended in flames, but from those ashes, a new philosophy of progress emerged. The material that once shocked Japanese engineers became the foundation of a civilization built on reinvention. By the early 1950s, American aircraft companies such as Boeing, Douglas, and Lockheed had integrated plastics into almost every system, from cockpit switches to insulation wiring. The dream of lighter, stronger, corrosion-proof materials now defined the future of aviation. The idea that had once seemed absurd, plastic as armor, became ordinary, and in Japan, the story came full circle. The same nation whose engineers had once stared in disbelief at resin brackets now led the world in polymer chemistry. Within a single generation, Japan produced cameras, radios, and automobiles whose heart was plastic. Molded, layered, perfected. The weakness they once saw had become their greatest inheritance. To historians, it was more than an industrial evolution. It was a change in mindset. The war had proven that the strongest weapon was not a tank, or a gun, or a plane. It was the ability to adapt. Metal rusts, empires fall, but ideas can be molded endlessly. By the late 20th century, nearly every piece of technology on Earth bore the fingerprints of that wartime discovery. The lightness of synthetic material, the fusion of chemistry and engineering. From the first transistor radios to the spacecraft that left the planet, all carried a trace of those 1940s innovations, a direct line from the shattered wreckage of Truk Lagoon to the modern world. In the end, what the Japanese technicians found among the wreckage at Truk was more than a new material. It was a mirror held up to the nature of human progress. Metal had defined the first half of the 20th century. Heavy, cold, unyielding. It built empires, ships, and machines of destruction. But plastic, light, flexible, and shaped by fire, came to define what followed. It was a material that forgave mistakes, that could bend without breaking, that could be reformed again and again. The Americans who molded it during war never set out to create a symbol. Yet they did. In their hands, chemistry became creativity, and necessity became invention. Plastic was the child of pressure, born from the fear of scarcity, and proof that freedom often begins not with abundance, but with imagination. For the Japanese observers who first held those strange fragments, it marked the moment they glimpsed the future. A future in which the power to transform would matter more than the power to endure. And for the rest of the world, it was the quiet beginning of a new age. An age not of iron or oil, but of ideas. Ideas that could be shaped, reshaped, and carried across generations like the molded resin of a forgotten bomber wing, still unbroken after the storm.